Welcome back to the Lowdown on Physics. This is Screencast 9.3 in a series on motion in 1 and 2 dimensions for Unit 3 BCE Physics. Today we're looking at uniform circular motion in the vertical plane. Before we continue, I'd like to just recall a few things about centripetal motion. Basically, first thing, if an object is moving in a circle, firstly it has to be accelerating and it must experience a resultant force that is always towards the center of the circle that it is traveling in. Okay, both the acceleration and the force are acting in the same direction. The speed would remain the same, but the direction is causing a change, therefore an acceleration and a resultant force. So centripetal acceleration, we have the formula A equals V squared on R, or 4 pi squared R on T squared. And force, same direction, we've got MA, or M times each of the equations for A, mv squared on R and M 4 pi squared R on T squared. So the question then is, once we start circular motion in the vertical plane, what's happening with the motion of the object? What changes will there be on the forces? We've got to consider gravity now because that's a factor. But to make things a little bit easier, we're going to look at the top and the bottom of the motion only. We're not going to have a look at, so here where we've got forces in one dimension, we're not going to have a look where the force is towards the center and gravity acts at right angles or any other point. So let's consider the forces on an object at the bottom of a circle. Here we've got a curve which approximates a circular motion path. We've got a radius of 2.5 meters and this car is coming down. What are the forces that are going to be acting on it? Obviously we've got a normal reaction force which is pushing up, and we've got a weight force. Notice the size of the arrow indicating that the normal reaction force is larger than the weight force. If they were the same, it would continue to move horizontally. It must be a greater net force when we add the two together, pointing towards the center in order to cause it to go around the curve. What would happen if, or what I like to do is think about what's it feel like personally if you're going through, when you're trying to work out which force is going to be stronger. When you go through the bottom of a dip and you're going quite quick, think about on the bottom of a roller coaster as it's sort of going down, you feel like you're being pushed down into the chair. You feel like your weight is greater, so you've got a larger normal reaction force. So let's have a look at an example. Now, net force here, Fn minus mg, is going to provide that net force, or that centripetal force. So for example, we've got a 1,000 kilogram car. It's traveling at 8 meters per second. Work out the normal reaction force. So if we look at our equation, the net force is, that's our centripetal force, mv squared on R, which is Fn minus mg. Now we're trying to locate Fn. That's a pretty typical exam question. So rearrange it. We've now got mv squared on R plus mg. Notice that we're going to add the two together, so it's going to be greater than your normal weight force, which is good because you feel really heavy at the bottom of that dip. Substituting in, we've got 1,000 times 8 squared over 2.5 plus 10 times the 1,000 for our mg, giving us a total normal reaction force of 35,600 newtons. The equivalent of just over 3.5 Gs. Now let's consider what's happening at the top here. We've got something that's approximating a curve here for a circle. We've got a radius of 2.5 meters. The car is now traveling over the top. When you go over that hill, your sort of stomach sort of jumps up into your, almost like it's in your mouth. You feel really light. So you expect that your normal reaction force should be smaller than your weight force. Okay, so you feel lighter, therefore you've got that normal reaction force that is less. So if we want to actually calculate what the net force is, here we've got F net, which is our centripetal force, equals mg minus Fn. Remember, F net is mv squared on r. Now what happens if you go too quickly? You actually end up getting airborne. If you're airborne, you've got no reaction force, and so you actually deviate from that circular path. So let's consider an example similar to what we did before. We've got the 1,000 kilogram car travelling at 2 meters per second. F net is mv squared on r equals mg minus the normal reaction force. So if we want to calculate the normal reaction force, we have to add Fn and then subtract F net, which is mv squared on r. So rearranging, we're adding that, subtracting that from our weight force. So expect it to be lighter as indicated by that, or feel lighter as indicated by the normal reaction force being smaller there. So substituting in, we get a normal reaction force of 8,400 newtons. Of course, if you go faster, that increases this part which you're subtracting, and therefore you get a smaller normal reaction force. This example's a fairly typical exam question. It's got multiple parts. It requires multiple applications of some of the physics that we've studied. The first part is effectively really an energy transformations question. So we've got the car, it's up here, it comes down to the bottom of the loop. What speed is it going to have here? So given that information, we look at potential energy into kinetic energy. Rearranging, divide by m, they cancel out, multiply by 2 gets rid of the half, take the square root, you end up with v equals the square root of 2gh. Now anytime we're doing that energy transformations thing for velocity down lower, you can actually directly go straight to that. Substituting in, we've got root 20, it has a velocity of about 4.47 meters per second. Find the centripetal acceleration. So we're at the base, we're about to start going around our circle. Given the information that we've got and calculated, we've got A equals V squared on R. So we've got 20, which was the 4.47 squared again, using the exact value, divided by the radius of 0.2, we've got 100 meters per second squared. So it's some pretty serious acceleration to get round that loop. Normal reaction force, well, F equals ma. We've got a mass of 0.1 kilograms, so we actually have a normal reaction force of 10 newtons. Speed of the car at the top of the track. So again, we've got more energy transformations. So the total energy it began with, let's start there, is mgh, so 0.1 times 10 times 1. It had 1 joule of energy to start with. The energy at the top of the loop will be a combination of gravitational potential energy and kinetic energy. So we've got initially 1 joule. The potential energy at the top, it's gone up a total of 2 radii, so up to 0.4 times 10 times 0.1 mgh, which leaves us with a half times mv squared. So rearranging, we end up with, that's 0.4, so we get 0.6 divided by 0.05, v squared equals whatever that is. Take the square root, we've got 3.46 meters per second. So in going from the base to the top, we've lost about 1 meter per second. Normal reaction force at the top. Now in this instance, unlike the example I looked at before, the normal reaction force is pushing down exactly like the weight. So both the weight force and the normal reaction force are acting towards the center. So our centripetal force, or our net force, is equal to the normal reaction force plus the gravitational force. So mv squared on r equals normal reaction force plus mg, or rearranging, it's mv squared on r, take away the weight force. So we've got a normal reaction force of 5 newtons, about half of what we had at the base before. And finally, the release height that will allow it to just stay in contact. Effectively, what this question is getting at is what height would you have to drop it at in order to come down and just make it around. If it was going any slower, it would actually drop off the track. So here we're actually going to set the normal reaction force to 0. So the centripetal force is entirely equal to the gravitational force at the peak. So mv squared on r equals mg, rearranging, so we're dividing by g, v equals the square root of rg. Minimum speed it has to have at the top is 1.41 meters per second. Therefore, find the total energy. You've got mgh plus a half mv squared, that's the total energy at the top. Substitute in, we've got 0.5 joules is needed. So now work back to an initial height, ug equals 0.5, we've got to start with that 0.5 joules, equals mgh to calculate h, so half a metre. And it would get around just touching it. The reverse to this, interestingly, we can use this same relationship, square root of rg, to find the maximum speed if it's going over the top. If you exceed that speed when you're going over the top, you actually get airborne. So this relationship can be used for minimum speed underneath, maximum speed over the top. Alright, that's it. So I'll see you in class shortly.